In this video, we're going to get into looking at the external BGP or eBGP routing protocol that makes a lot of the internet actually work. So when we refer to things like BGP, there's a couple different versions of it. There is internal BGP and external BGP, but every time we say BGP, I'm just going to have you think of external BGP. So this has been quoted as the protocol that makes the internet work. So a little bit about the history of this is kind of back in the 90s when the external routing was really taking shape. BGP came out as the forerunner for being a very simple protocol and also very scalable, easy to implement, and is now the protocol that we use across the board. So if you are traversing the internet, going across your ISP and connecting to really any other ISP or large organization, I would almost be willing to bet here that you're going to be reaching across to that network with BGP. So there really are no other alternatives on the public internet, which makes it a really important protocol to have a bit of understanding about, and you'll find that the complexity and stuff of it really isn't too bad. It's just a popular, scalable, pretty flexible protocol that we're going to use. So some of the things that it does have is it has quite a bit of security features built into it that we can use. The truth is not everyone is using those. So there's things that we can do with BGP like route filtering, we can do MD5 authentication, and we can kind of pick and choose our neighbors a little bit. And there's also other implementations to kind of help monitor the state of BGP. We'll talk more on the security stuff a little bit later on. But for right now, just getting into how does this thing actually work. So when we're talking about BGP, it is a exterior gateway protocol. A lot of the stuff you probably have looked at before, like OSPF and EIGRP, maybe even RIP, those are all your interior routing protocols, and they're designed for speed. I want to know how to get to that endpoint as fast as I possibly can. Let's make a self-healing, really dynamic network, and that was the focus of internal routing protocols. With BGP, we're not so concerned about the actual speed of convergence and things like that. What we concern ourselves more about with BGP is actually choosing the path of how our traffic gets from point A to point B. So we're going to use that path selection, like I said before, to route between different autonomous systems. And remember, these autonomous systems are generally a collection of routers that we own, something under our control or our domain. And typically when we think of BGP, we're talking about ISPs and larger scale environments. So what we're going to look at here is just a normal network here and no need for BGP. This is a pretty typical setup that you might see. We basically have a customer, an ISP, and the rest of the internet out there. From the customer's perspective, they have a couple of servers, and they probably get their IP addresses from that ISP. So more than likely, maybe a handful of static IP addresses. If they just had one static IP address, they could put those servers behind NAT. But the big point here is that this customer is only connecting to one ISP. So at the end of the day, it really doesn't matter where that traffic is going. If it's leaving the customer's network, the only place it can go is that single ISP. So think about this, between the customer and the ISP, there really is not a need for a routing protocol. The customer sets up a default route, shoves all of that traffic to the ISP, and then lets the ISP figure out where to send the traffic to. Let's take a look at a different example. So something you might be thinking about here is, well, what if we have redundant links up to our ISP? Really, at the end of the day, same process as what we looked at before. The customer's traffic, although it has two routers to get to that ISP, the only way that traffic can go is destined to the ISP. So what we need to do in this case is we could create two routes. Maybe that top pair of routers has the preferred route, and the bottom pair of routers could be a backup or a secondary route just in case the primary failed. And you could talk about different things like load balancing, maybe doing a 50-50 split or a 80-20 split, whatever you decided to do. But the point is, again, traffic is leaving your network. It only can go to your ISP, and from there, it gets routed out to the internet. When we talk about places that will need actual routing protocols like BGP on the public internet is just one more example, and that's where we connect off to multiple ISPs. So in this case, we still may have a preferred ISP, but there's a lot of questions that come up, and it's something that we have to kind of think about critically. So number one, think about where does that customer get their IP addresses from? Do they subscribe to the IP addresses from ISP1? When that fails, they subscribe to the IP address assignment from ISP2 and have to flip things? Probably not. Of course, that would be a little bit of work and overhead for the administration when a site would go down. So how do we know how to get to that customer? Well, this is really where BGP comes into play. So what happens in a situation like this is pretty common. So we might have two ISPs if we're a high availability system, and we want to make sure we're going to be up and ready for anything that might happen. So what we're going to do in this situation is we will go out to the IANA, or an organization like ARIN, get a block of IPs that we actually own, and then we'll advertise to those two ISPs that we now own block number X of IP addresses. So rather than getting the IPs from the ISP, we go get them ourselves, and then we tell those ISPs about them. In that way, those two ISPs can make routes saying, if you're trying to get to this customer's network, I know how to get there. If you want to take a look at this, this is the assignment from Aaron on the DSU network. So it's kind of interesting. If you look at this, you can just go right out to whois.aaron.net, and you can look up your IP address and figure out where those allocations came from. But what you can see here is that DSU has a 138.247, and that's a slant 16, so we know that's a Class B network. DSU didn't get that Class B network from an ISP. As you can see underneath the net type, it's a direct assignment. So they went out, bought that block of addresses, assigned them to their equipment, and then negotiated and talked to those ISPs or those different service providers and said, this is our addressing scheme. You guys need to set up routes to connect to us. And what that process kind of looks like a little bit here is two ISPs or autonomous system and an ISP enter into some sort of agreement to route traffic to and from their respective autonomous systems. So they've talked to each other and said, we want to route traffic between each other. They sign some contracts, let the legal teams figure everything out, and then go talk to the network administrator. So the network administration teams coordinate with each other, and they both stand up BGP. And part of BGP is that we have our own autonomous systems. We also have what's called a autonomous system number. And that'll be a unique number tied to our autonomous system, and they're going to be unique across the entire internet. So what we end up doing is we figure out who each other's autonomous system numbers are. We plug that to our router. The routers start talking over TCP port 179. BGP is actually a layer 4 protocol. So we're going to communicate over TCP 179. The first time they boot up, they're going to exchange the entire routing tables that they have. After that, BGP just sends updates. BGP is a really interesting protocol in the sense that we do that convergence once, right when the routers are booting. And after that, it's a non-discovery protocol. We only see updates as they get pushed to us. We're not constantly looking for changes and things like that with it. So let's talk a little bit more about the autonomous systems here. So as I said before, an autonomous system is just a collection of networks, routers, equipment, things that you own under a single administrative domain. And really the only exterior gateway protocol that we use is BGP. So if you're talking about the public internet, you're talking about those collections of ASs, you're talking about communicating with BGP, and then that brings us to the ASN. So much like we have to go buy IP addresses from Aaron, we can go buy a ASN number or register that with those public authorities, and then we own that number. If you're curious about this, go to www.whatismyasn.org. It'll just give you a nice little printout of what your actual ASN is. Some of the other interesting information that this website will give you is the BGP path that you took to get to that website. So you can actually see the ASNs of the peers that you traversed while trying to get to that website. And that's really how BGP works, is it's a path vector protocol. We'll talk about that a little bit. If you wanted to go take a look at some of the prefixes and ASNs that are registered out there, put this website in here for you too. So just cider-report.org/AS2.0. And this will let you look up some of those different ASNs and what net blocks that they belong to as well. So it's all public information out there. There's nothing really to be hiding with it. It's just interesting to look up, and we need to know those paths anyways. So let's talk a little bit about BGP and how it takes into account different attributes to make this routing and make this thing actually happen. So one of the most important things about BGP is your autonomous system path. You'll see it abbreviated as AS_path in all caps, typically when we're talking about the configuration of it. What this is it is the listing of autonomous systems that you need to cross to get from point A to point B. So if you want to think about it in a way like RIP, where RIP was talking about hops and trying to get from point A to point B based off of hop count, one of the vectors that BGP takes into account is just that same thing. How many autonomous systems do I need to go through in order to get there? There are some different things that happen in BGP that can change the weight of a route, so changing how desirable a route may or may not be. And some of those things might be like local preference. So this is kind of our internal cost of a destination. So how do we really get there, and what's the cost specifically to us? And that lets us get a autonomous system-wide consistency. So computers in different parts of our network might have different costs, but we're trying to keep that consistent and really figure out the best path overall. There's multi-exit discriminators, and what this is actually basically doing is saying we might want to prefer one of the ISPs over another. So if we're connected to two ISPs, I might say ISP number 1 is preferable over number 2, so I can change the cost of that and say you need to go out ISP 1 if it is up and available. So we can kind of change the weights of things that way as well. And lastly, we have as well communities. So these are just basically generic tags that can manipulate different administrative policies. We'll get into a little bit of that more later when we actually get into the configuration of this kind of stuff. So a few more properties of BGP. It does share pretty similar concepts as EIGRP in the sense of we have to establish neighborship. The difference between EIGRP and BGP is that in BGP, we know who our neighbors are. We have to figure out what their ASN is and plug that into our routers, whereas EIGRP will actually discover the neighbors automatically, but the principle of having a neighbor is still the same. We learn about routes from our neighbors, so when things go up, come down, new networks get stood up, we're going to learn about this from our neighbors. We have a routing table, just like in EIGRP, so we're going to keep track of all those routes. BGP does keep track of the different paths that it can take, so sort of the feasible successor routes or backup routes in that sense. And we're always, of course, going to go over the best route. That's just kind of a given with most of the routing protocols that we look at. So if we're going to set this thing up, we need a few settings at a bare minimum. You need your router's own autonomous system number. And again, this is something you would have retrieved from a central authority somewhere. If you're doing internal BGP, of course, just make them up. It doesn't really matter. But the big important part here is that all of these ASNs have to be unique across the internet here. Once you know that, you also need to know the IP address of each of your neighbors, and you need to know those neighbors' ASNs as well. So this is going to be contributing to that static development of neighborships that we're going to make. So for two ISPs that want to partner, we're going to exchange routes, build more of a web network out there, we're going to need to know what their ASN is, are they willing to participate, what their IPs are of their routers, and then we're going to actually have to configure all of that on our own here as well. So if we took a simple network like this might be an example of an enterprise connecting out to a couple of different ISPs here. We'll just talk about a couple different things this way. So if we're looking at the enterprise, we see that is clearly ASN number 11. And we have ASNs 1, 2, and 3 matching the ISP 1, 2, and 3 respectively. The connection between the ISP 1 and our enterprise is two T1 lines, and those are connecting over these serial interfaces. Those are going to be considered the primary connection, and the enterprise 1 also has a connection out to ISP 3 as a backup or a secondary connection that way. So what happens here is when the topology updates and ISP 1 and enterprise 1 all synchronize their routing tables, they've done a full exchange with that. ISP1 is going to advertise default route plus all of its updates back over to the Enterprise 1. So in that case, the ISP1 using ASN1 will talk to the other routers here as well. So ISP3 will also advertise a default route and partial updates that only include customers local to ISP back to our ASN, number 11 there. So what that means is if the enterprise wants to talk to a customer on ASN3 and that customer only exists on ASN3, ASN3 will be able to push an update or a route over to our enterprise. Everything else that's not just specifically local to that ISP3 is going to come in from ISP1. When we're doing these peer relationships, so when we're talking to our neighbors and establishing those adjacencies, each of the ISPs is going to use the lowest IP address, or the IP address of its lowest numbered interface to create those relationships. So kind of briefly looking at what the configuration might actually show. We can see here on the E1, that was our enterprise, or the network we might own. We just establish it with router BGP 11. That is our autonomous system number. We tell it who our neighbor is, so 10.1.1.2, and we can see from the picture here, 10.1.1.2 is the lowest numbered interface on the ISP1 router. Okay, so serial 0, of course, lower than serial 1, so that's the interface that makes the connection with. On the ISP, same type of thing there. They're going to say they are router BGP 1, so that's signifying autonomous system number 1. They tell it who their neighbor is, so 10.1.1.1. Well, if we look back again, 10.1.1.1, that's just the other side of that serial link, and that is our interface on the enterprise. Last thing that we have here is just to connect up on the ISP3. So we're saying really the same thing there. Router BGP3 just means they're on ASN3. They tell us how to get there, or who we are to them as a neighbor. So we are 192.168.1.1, and our autonomous system number is just 11. So you can see it all there. Our serial 011, that is the 192.168.1.1, which is the only connection we have back to ISP3. So hopefully not too complicated there. Big picture that you need to just realize is that we have to know our neighbors' ASNs, we have to know what IP address to plug in for them, and that IP address should come from the lowest numbered physical interface on that neighbor. So moving on a little bit, a couple things that we need. If the BGP router IDs of the two routers cannot be the same, we'll talk about where the router ID comes from. If we decide to configure it, we have to have our MD5 authentication pass, so meaning we have the same keys being accepted on either side, or valid keys being accepted. And each of those routers must be part of a TCP connection with the other router using that remote IP address. So you have to be able to ping it or communicate with it some way over TCP. And we can see that's evident because these route updates exchange over TCP 179. So pretty fundamental. If we don't have that TCP port there, those routers will never talk to each other. So where does the router ID come from? Well, there's a couple different ways we can get a router ID. We can statically configure it, and that's just like what we saw with OSPF and EIGRP, where we can actually just manually set the router ID. Your second option that you have is creating it with a loopback adapter. So the highest numeric IP address of any up loopback interface will be the one that the BGP process uses. So very similar to what we saw in EIGRP. And then of course, last thing we can do is the highest other interface. So if you have an IP address on an interface that is up and it has a connection, if it's not a loopback, that'll be the last thing that BGP uses. MD5 authentication is pretty simple. It works a lot like EIGRP in the sense that we have our neighbors, we need to know their IPs, and we'll agree upon some passwords or a keychain. Basically, long story short with the MD5 authentication, it has to pass if it's configured, otherwise our routes never make it, or simply if you don't configure it, you'll just exchange with those uninhibited as well. So the TCP side of this, we talked about a little bit, has to be there. We have to have TCP connections in some fashion. So the way this looks is our neighbors first form a TCP connection. In all of our BGP messages, those route updates, the table synchronization, everything like that has to flow over the connection. And so because of the way that TCP works, we have the SYN, the SYNAC, and the ACK, our three-way handshake. We know when those connections get established, and we know when those messages arrive at the neighbor and when they didn't. So that's one way that we can keep track of, are our neighbors still alive, are their interfaces up, and can we communicate with them? In this image, we've got a little bit different setup here between a couple of the routers. So it's just a smaller view. We still have E1, that was our enterprise, and then the I1-1, that was the ISP number 1 router there. So just looking at the connection that we have here. So the process of what's actually happening in here, if we just kind of follow the numbers around the diagram, at number 1, our E1 router is going to find the neighbor 10.1.1.2 command. So E1 will send a BGP message for the neighbor inside of a packet with the destination IP address of 10.1.1.2. And we should know from that previous diagram, 10.1.1.2, that was just simply the IP address of that ISP1. So we figured out who our neighbor is. We need to create a packet with it and send it off to that neighbor. We're at our next step, number 2 here. We're going to look in our routing table for a route that matches that destination of 10.1.1.2. So looking for a route pointed to our neighbor. And then once that route is matched in step 2, we will list our serial 000 as our outgoing interface. So how do we send that traffic that way? So our IP address on serial 000, as you can see, is just 10.1.1.1. So that's going to be our source IP address. And the neighbor command on the other router, the ISP router, will refer to our source IP address, which is 10.1.1 in this case, to make that link and send that traffic back the other way for BGP. So just a few more things here with BGP that we'll talk about in the basics of it. Typically what we have is, if we just have a single layer 3 path between two neighbors, so just one physical connection between two neighbors each, it's not going to be a problem that way. If we have multiple paths between those ISPs like we looked at in the previous example there, we're going to use the interface IP address for the connection. If we use that IP address for our connection, that link fails, BGP is pretty much going to not handle that very well at all. So if we lose that one neighbor command that we made saying our neighbor is on IP address 10.1.1.2, our link dies between that, we need to have that backup BGP route configured so we can just fall back to that. So there's a couple of solutions that we can do to fix this problem. Number 1 would be we can just configure 2 neighbor commands on each router. So we set up the connection to 10.1.1.2. We could also go back and just take a look at this diagram for a second. So looking at our top link here, serial 000 connected to serial 000 between enterprise and ISP1. We configure a neighbor command for that top serial link. We'd also configure a neighbor command for the bottom serial link as well. So talking about those serial 001 interfaces. A little bit more work, but of course it would certainly work if we wanted to do it that way. The other way we can do it is pretty cool. We can actually use our loopback interfaces as the endpoints for this. So a loopback adapter we know will always be up. There's really nothing for it to connect to, so it shouldn't ever be down. So we can change our BGP update source from a physical interface to a loopback interface. And when we actually need to exchange information with BGP neighbors, we will just route the loopback's traffic over one of the valid connections that we have to our neighbor. So the source being the loopback, we never have to worry about that changing or going down. We'll always trust that we can get to that neighbor in some way or the other. What the configuration process of this looks like is we'll basically just put an IP address on the loopback interface of each of the routers. We're going to tell BGP on each of those routers to use that loopback IP address as the source IP address. So when we do our neighbor update source command, we'll see that that loopback adapter IP gets stuck in there. When we configure the BGP neighbors, we'll just tell each other's routers that you need to connect to me on the loopback IP address, and everything should pretty much work out okay after that. So what we need to have is that each of those routers does have a route, so we can forward packets back and forth to the loopback interface using the actual real IP address of the other router. And we'll configure these as a multi-hop thing. So what the multi-hop does is basically BGP wants to use a TTL value of 1 when we're talking to our neighbors. Well, if we have to traverse a loopback and a physical interface, that's 2 hops. So we just need to bump up our TTL value. And that's all that eBGP multi-hop command is doing. So what this looks like at a high level, on router E1, that was our enterprise talking to the ISP. We're going to assume that the loopback adapter has an IP address of 11.11.11.11. And in the configuration of that router, we're just going to tell it your update source is now the loopback adapter. And that's really all that we need to do here. On the ISP, they'll say the neighbor is our loopback IP. They're also using a loopback adapter as their update source. So it's going to be a loopback to loopback connection. But if we configure it the same on both ends, all of that traffic should go across and everything will work out that way. And so here's what we're talking about with the multi-hop concepts. Like I said before, the big picture here, BGP uses a TTL, or that time to live value of 1. When we use the loopback, we just have to bump that up by 1. Otherwise, we'll never make it through there. So just getting down to last of the real big concepts that I wanted to cover, at least at an introductory point to BGP, a little bit about the redundancy and some of the authentication here as well. So we've kind of discovered some of the problems we might have with redundancy, whether we want to load balance, whether we want to prefer a path over the other. If our primary neighbor link goes down, do we have a secondary one to back up to, or are we using loopbacks, all of those types of things. So the next thing that we should really talk about would be our authentication keys that we're going to use here as well. So if both those BGP routers use the authentication key of Fred, basically every time we send a update or when we receive an update, we're just going to send the update signed by Fred or using that key. And assuming that matches, we should be able to configure that redundant path, or really even if it's a singular path using BGP as well. Configuration on that is pretty simple. All we see here, really in our BGP, the only thing that we're adding is this very bottom command here. So we've already talked about the loopbacks. We've talked about setting up just the normal static routes on there. So we just added on password Fred to the bottom. You'll see the same thing on your ISP router as well. So just adding on the multi-hop and your password of Fred at the very bottom. So that's all I wanted to cover here. BGP is a really big animal, as we can probably start to imagine, being that it is the routing protocol for public internet. So we're going to leave it at that for an introduction. We'll look at some configurations as well, and then we'll dive into some of the bigger concepts of BGP and also a lot of the really interesting security vulnerabilities. So there's been some pretty big BGP attacks, some pretty high profile ones. We'll try to dive into that a little bit too and kind of drive home the point that we need to be thinking about BGP securely, and not only that, but what we can do to better BGP down the road as well.